We are very pleased to introduce you to Christopher Vella, who will be talking about easy LPEs and common software vulnerabilities. So let's all welcome Christopher to the stage with a big round of applause.
Thank you. And so my name's Christopher, and I'm here to talk about a lot of the common vulnerabilities in software that I find today, and how some of them are very trivial to do things like privilege escalation on modern Windows. As a day job, I'm a security researcher at Microsoft, where I write fuzzers for the Hyper-V hypervisor. And I've got my Twitter up there as well, where you can shoot me questions about this even after the talk. And I guess a bit of background as to why I want to present this information. During work and even in personal time, like before even getting into vulnerability research, a lot of the talks that I've seen revolve around things like complex memory corruption vulnerabilities, or things that require like maybe 3 months, 6 months plus of deep reverse engineering effort. Things like dealing with custom hypervisors for fuzzing, emulators for fuzzing, all these kind of complex environments as well. And one of the common things I heard before knowing anything about vulnerability research, starting out my career in security in general, was kind of this complexity around vulnerability research and how finding 0 days is getting harder and harder, especially with the advent of mitigations like ASLR and DEP and things like that. And when you browse like ZDI and advisories like that, you see heaps of software vulns coming out in common software like Adobe, and that day after day. And you think that, you know, these sorts of things are being looked at or being fuzzed by large companies with resources of like 500 plus cores in the cloud, and they're just fuzzing away on all these sorts of things. That kind of leaves not much room for, I guess, vulnerabilities that are very simple and easy and can be potentially quick to find for people who are just getting into the space or aren't as experienced. But from my experience, there are entire categories of vulnerabilities, not just like a bug that's not exploitable, that's useless and no one cares about, but actual privilege escalation bugs in these prominent software that go unnoticed and you can find pretty easily even today. So that kind of set out a set of goals for the types of bugs that I wanted to find and how I wanted to find them as part of this little, I guess, exercise. And the goal was to find them fast, find 0 days fast. I don't want to spend, of course I could spend months reversing something, writing a fuzzing harness for it, or just manually understanding its logic, mapping it out, things like that. But I wanted to find bugs that I could discover in hours or days, maybe even minutes. I mean, one of the 0 days that I'll be demoing later, I found in maybe half an hour of looking on a system, if that. So some of these, if you know what to look for, are extremely easy to find, and they're also easy to exploit. You can go from bug to actual exploitation and get that priv-esc, for example, in a very short amount of time. That kind of trials into the speed thing. I don't want to, well, for this exercise, I didn't want to find a bug that would then take me 6 months plus to actually have an exploit in. So we're kind of focusing on speed here. And when I think of these bugs, I think about like the bugs that I would have enjoyed knowing about back when I was doing red teaming, for example, where you have like limited time on engagement and you want to priv-esc on a box and you don't really have the luxury of spending weeks and months diving deep into research. So these are the types of things where you could potentially find these bugs very quickly and use it even live on an engagement. And I'll be demoing these towards the end of the slides as well. So that kind of leads naturally into focusing on logic vulnerabilities, mostly because we're targeting, like in my examples, we're targeting modern Windows 10. So a lot of the, if you go for memory corruptions, you're likely going to have to deal with things like ASLR and DEP, or if it's a heap exploit, you're going to have to focus on heap grooming, and all those things just take too much time to turn a bug to an exploit for the most part. So I kind of wanted to focus or believed that I had more luck focusing on logic vulns. And this also ties in to how lots of people do vuln research, especially companies like Google Project Zero and that, or OSS Fuzz and that, would focus on fuzzing or finding bugs in Adobe, or finding bugs in anything else. You do get the logic vulns there still, definitely. But a lot of the vulns you'll see will be memory corruption vulns. There will be things where they can write fuzzes for, spin it up in the cloud and run that for like 3 months plus, which does make it a little bit more difficult to find memory corruption vulns, although I will say there are still plenty of memory corruption vulns in lots of software to find. So it's not so much the lack of them, but more so for speed that I decided to focus on logic vulnerabilities. And when talking about logic vulnerabilities, there's lots of types of logic vulnerabilities, things from like read permission checks and things like that. One of my favorite ones is bad assumptions, which is kind of a very broad category, I guess. But one example of it that is very, very common is related to file I/O. So an example here, a little snippet, right, where we're opening a hard-coded file path and writing to it twice. An assumption here may be that that file being opened is the exact same file in both cases, or even that that file actually does live in C drive program data my folder, which I guess technically may be the case, but due to the fact that Windows and other modern operating systems have file redirections in the forms of symlinks and junctions and hard links and things like that, C drive program data my folder could potentially redirect to C drive Windows System 32. And then suddenly your file1.txt that you're opening actually lives in System 32, not in program data as expected. That's just an example of like an assumption that a program may have that could be a security vulnerability if it's something that they haven't sufficiently accounted for or thought of. And so, in general, when looking at what's in a zero-day, there's a few components, right? We need to have a component to interact with. So if we take this snippet, for example, like the print spooler service, we need some way of interacting with that component via some method, maybe some sort of IPC, shared memory, file I/O, something like that. And then some sort of internals knowledge as to how we can abuse some of those behaviors via a symlink redirection or some other logic issue, and then how we can turn that into a bug. And when we're looking at the interaction part, there's lots of common attack surfaces in processes, and this mainly relates to how processes interact with each other. For example, if I were to install an antivirus on my computer, most of the time it's not going to be just one executable and that's it. Typically there may even be like 5 EXEs and a few drivers and various other components that get installed alongside that. And they need some way to interact with each other. That can be via COM, RPC, shared memory, name pipes, just file I/O in general, device drivers, and various other mechanisms. And all these ways of communicating between processes can also be leveraged for, say, an unprivileged process that we create to interact with a more privileged process running as system, for example. This all obviously depends on things like what permissions are set on things like these name pipes or these shared memory sections that will determine if we can interact with them and how we can interact with them. But they are definitely a lot of common attack surfaces that I see in a lot of software. And commonly you'll find that this software doesn't adequately have permission checks in place for these sorts of things. And when it comes to Windows, we're kind of lucky that a lot of the tooling for finding this attack surface and enumerating it is public already. We have like Process Hacker listed, we have tools from Google Project Zero in their sandbox attack surface analysis toolset. We have the sysinternal suite as a whole, which is a great set of resources as well, and lots of other open source or public resources for enumerating these attack surfaces. And I'll give an example of that a bit later as well. Now, I kind of touched on the file system redirection stuff, and I have a few demos later, and they're not all based on file system redirection, but I feel like this kind of needs to be pointed out again, simply because this is super common. This is one of the most common things I find in software, where they, I guess, don't have the understanding, or there's oversight, or some reason they do some sort of file I/O in an insecure manner, simply because we can have control over redirection of these paths. So as an example, C drive itself is a symlink. We as a user can change C drive to point to C drive temp, or change C drive to point to a different drive altogether. Every folder path could potentially be a junction that just redirects to another folder, and every file could potentially be a hard link to another file. James Forshaw had a good talk on a lot of these file system redirection components in his talk called A Link to the Past, roughly around 2015. So it's definitely not even a new attack surface. And if we start thinking about this sort of thing, we also see that it's not unique to Windows. So while I am talking about Windows in this talk, macOS and Linux all have file system redirection capabilities. I've had vulnerabilities in Mac where they use certain APIs to get the path of their application bundle, and that typically is expected to live in like /applications where low privileged users do not have permissions to write to. But by utilizing hard links and creating a hard link from a less hardened folder, we can trick that API to returning a different path, like /temp or somewhere in the user's home directory, where the user does have full control over that file. And the application doesn't know any better and does something silly and insecure on the assumption that the only path it's going to return is like this /application /myapp.app bundle path that's really hardened. But that may not be the case. So it's definitely not a set of vulnerabilities unique to Windows. And when we start looking at junctions, we can see that these types of vulns are actually really, really common. I have a little scrolling thing here. It's not scrolling, but anyway, if you go on ZDI and you just search the keyword junction, in the past few months alone, you'll find heaps of vulnerabilities reported in core Windows itself and third-party products. And when you see these types of vulns affecting the core Windows operating system on such a level, you kind of realize, or maybe have an intuition, that these types of things are also going to affect third-party products a lot. It's kind of a natural assumption when you see that how badly it's affected by Windows. And Windows has kind of mitigated some of these things. If we go back to the whole potential hard links, there was hard link mitigations released in the Windows OS not too long ago. And in the future, I expect there to also be mitigations against a lot of these junction attacks that we will see shortly. But currently, it kind of does plague a lot of software. And one example of that I'm going to demo is related to Zoom. I'm sure everyone's familiar with what Zoom is, especially during COVID times. So one of the bugs, so this example, for example, is going to be a junction-related logic bug in Zoom that we can turn into a privilege escalation 0-day for Zoom. So let's see if I can get the demo showing. Okay. Just FYI, the VM that I'm using to demo these is just the MS Edge developer VM that you can grab off Microsoft's website. So I pulled that down and just ran that as is. I installed a few extra software packages on them, things like Zoom as an example, and some other products that I'll be demoing. And just as a quick view of the attack surface stuff I mentioned earlier, if we open up something like Process Hacker, and then we open up just some random process, we can automatically see things like, okay, it's got RPC ports, it's got events that we could potentially interact with, it's got handles to device drivers, which are also a potential attack surface, depending on if we, as a low-privileged user, can interact with this device driver. We have, under files, there'll be file I/O stuff, but there'll also be things like named pipes, if it has named pipes opened. And there's also things like, if I scroll down, memory sections that we could potentially map into our own unprivileged process and modify. And these are all potential attack surfaces to this process, depending on how this process interacts with that and what the permissions are set for that. That's kind of like a little example of just a very quick way to enumerate something relating to attack surface on a random process. So with Zoom, for example, I have Zoom here. Should have been updated a few days ago, so still a 0-day. And this one, we need some way to get Zoom to do something insecure. One of the things I like to check is when Zoom is installed via like an MSI package and things like that, the installer lives in C drive Windows installer. And these are interesting attack surfaces. If anyone's seen Sandbox Escaper's work on Twitter, she has done a lot in this space as well. And previously, James Forshaw has also done a lot, like I said, relating to lots of these symlink-related vulnerabilities. And so one way to identify if an MSI belongs to your target, I like to just look at the digital signature, right? I see Zoom there, so I know it's Zoom's. That's simple enough. And then if we hit right-click and repair, the nature of the Windows installer is the Zoom MSI is going to run and it's going to do a certain set of operations to repair itself. But the key point here is that when the MSI runs, it auto-elevates itself to system, even if we are just a regular user. So whatever it does in that MSI package has to be careful in a way, since it is operating as system. And if I look at a Procmon trace, actually, let me start another Procmon session. So if I start Procmon to capture and I run repair on the MSI, the MSI file, like I said, Zoom will auto-elevate, do stuff, whatever it's coded to do. Usually just either checking file hashes, moving files around, general kind of repair operations like that. Let that go. Let me check my filter. Yep, I need to remove this. And now we can see all the various operations that it did. And typically for vuln research, you know, if you see your target has Zoom installed, you'll install it locally and do these sorts of things on your local machine to identify. And if I scroll down, we'll see certain interesting behavior. Let's see if I can spot this one. It does a lot of things. I think I need to adjust my filter again. So what we should see is it trying to do something in our... Here we go. Okay, found it. So instantly we see here that this process, which is running as system, is trying to access something in our user's app data folder. Now, since this is our user's app data folder, we have full control over the contents of this directory. Well, at least in normal cases, we have full control over the contents. That may not necessarily be the case, but in most cases it is. And it's trying to access these folders, right? bin 0001, whatever, but it can't find it. So the thing that pops in my mind is, what if I create this folder? What is it going to do next? It might try to do something silly, like load a DLL from there. If it does, then that's probably an instant win for us. So one thing we'll do now is we'll go to that folder. We see that there's no bin. I'll make that directory. And just for now, I'm going to include just that path. Actually, that didn't work, but that's fine. We'll restart or rerun the repair operation, which we can just do as many times as we want. It will run through again, and we'll be able to see what it tries to do with this directory. Let's just exclude this. Still doing its thing. And these types of things where it tries to access files or folders in folders that we control are nice things to look out for. Okay, so we see that it accesses it, and then what it does afterwards is it just deletes the folder. So if I go here, we can see that bin no longer exists. It just deleted the folder. You might be like, okay, it just deleted it, so what? But the thing is, since we have the capability to do file system redirection, we can actually leverage this to trick Zoom to deleting any folder on the system we want, which means we have an arbitrary folder or even file deletion primitive here. And that is something that we can leverage to turn into a privilege escalation exploit. There's ways to do it with the core Windows operating system itself. There used to be tricks with the Windows error reporting folder. Now there's tricks with Windows Defender. And I kind of encourage anyone who's interested in these types of things to find other methods as well. But when I was running through these demos a couple of days ago on this VM, I found something else interesting that stood out to me that I figured would be more fun to demo as well. And that's the fact that this VM on the Microsoft website comes pre-installed with Chocolaty, the software management package, I guess. I haven't really used it myself, but it is installed on here. And one thing I realized that's quite interesting that allows us to leverage this deletion for a privesc is the fact that if we look at the system environment variables for the system path, we can see that C drive program data Chocolaty bin is a path in the system path, which means there's going to be a lot of system or applications that run a system that are going to look into this path to find a certain DLL that it's missing and things like that. And another key point about this path is that it lives in program data. It's in C drive program data Chocolaty. And why that is so interesting is the fact that regular users can create folders in program data. I can do make dir temp, and temp is there, as an example. Any regular user can create a folder in program data. It's not a lockdown folder. And in Chocolaty, we have the Chocolaty/bin, which is in the path. This folder is locked down. I can't just create a DLL here and hope that a system process loads it. If I could, that would be an easy privesc again. But the very fact that it lives in program data and we have this arbitrary folder deletion, what if we just delete the Chocolaty folder, create our own Chocolaty folder with its own bin, and since we created it, we have control over its contents and we can put whatever DLLs we want in there. And that's exactly how this type of thing is exploited. And I'll actually demo that. So as an example, so this shouldn't have been run before, so I shouldn't be able to delete Chocolaty. Access is denied. Obviously, it's still there. I tried to delete everything, didn't work because the ACL is restricted. So when I think about how to exploit this Zoom vulnerability, let's go back to our app data Zoom. Let's delete the Zoom folder, make it as an empty one. And the tools I'm using here are from Google Project Zero's symbolic testing tools that are on GitHub. And so if I go to my users package for that, and I go create mount point, and I say, let's turn Zoom into a mount point that points to RPC control. And then let's create another symlink from RPC control/bin, and we point that to our directory that we want to delete, which is program data / I can make this bigger, program data / Chocolaty. So hope I spelled that right. So now if I dir on Zoom, it's going to RPC control, which is nothing. But if I dir Zoom /bin, it should go to our Chocolaty folder, as it showed there. So now that we have that, and we can see that zoom here shows that it's a junction to RPC control. And now all of this is done as a low privilege user. So now if we go back to the MSI, rerun the repair operation, if I go to C drive program data, we see Chocolaty here. At some point, thanks to the folder redirection, Chocolaty should disappear. Shouldn't take too long to happen. Just give it a few steps. Bam, Chocolaty is gone, right? And now, thanks to that, we can go into program data, make the Chocolaty, bam, go into Chocolaty, make the bin, cd bin, and suddenly now we can write here whatever we want. And now, since this is in the system path, the next step to turn this to a privilege escalation is to find a system process that's going to try to load something from this directory since it's in the system path. And I have a process monitor trace from boot that will show us something that does that. So if we capture a boot trace, which you can do by just going options, enable boot logging, we'll see that the Spoolsv process, which runs the system, tries to load or tries to create a handle to this tpgen lic.dll in this Chocolaty path. So if I copy over our own DLL to here called, what was it? tpgenlic.dll, right? That DLL is here. This DLL that I created will simply create a file in C drive. In C drive, we can create folders, but we can't create files, right? If I go test.txt in C drive, access denied. And the DLL that I planted, if it runs, it'll create a text file in C drive called itworks.txt. Simple way for me to just verify that it executed code. So now that we have this planted in program data, well, in Chocolaty actually, all I need to do is get the Spoolsv process to reload. There could be various ways to do this. The easiest way I'm going to do is just restart the machine. But you could potentially restart the service. You could even, there's bugs where you crash the service and then it just auto runs again since it detected that it failed. Some things, when you exploit these on core Windows, aren't even things that you need to get a service to do. It's something it'll do periodically maybe, like every 5 minutes it'll do this operation. Or every time you update, Windows Update or some sort of signature database, it'll do this operation. Okay, so we're logging back in. And now, based on our Procmon trace that we had from the boot logging, we expect that Spoolsv would still try to load that DLL that now suddenly exists. And if I just go to C drive, try to make it a bit easier to see. Oh, what do you know? Airworks2.txt is suddenly there. Hello from system. Bam, you got privesc in Zoom. And that's just kind of one example, right? This is a 0 day, and actually one other thing I'll mention is that Zoom bin deletion is just one of the ways you can trick Zoom into deleting things. There's like 3 other ways that I found as well. And for example, this can be found by just opening up Procmon, knowing how to set your filters, right-clicking an MSI, hitting repair, and then finding it. Like I think I found this in about less than an hour of just downloading Zoom and playing around with it and seeing what happens. So these are definitely the types of vulns that once you're aware of, you can start seeing them everywhere. Another example I have, so this one isn't a 0 day, this one's an end day. I found this one earlier last year, and then someone else found it again earlier this year on Twitter. So it kind of was fresh in my mind. And this one's an interesting one because it's not a file redirection one. And anyone who knows Foxit PDF reader, or I guess PDF readers in general, they're heavily fuzzed, right? If you search for Foxit on ZDI, you'll find memory corruption vulnerabilities reported practically daily, weekly, over the past X amount of months or years. It's something that's heavily fuzzed. Yet they lived in there, one of the most simplistic logic bugs that you could easily turn to an LPE ever. And I'm going to demo this one now as well. So I have the older version, it's not that old actually, but the vulnerable version of Foxit Reader. Oh, I've got to close the presentation and go back to that. And one thing Foxit Reader does when it's installed is it has this Foxit Reader update service that runs as system. And I believe I already have a Procmon trace of it. Actually, I don't need to. I can just open a new one because it runs like crazy. So this one, as soon as you open Procmon, it stands out like crazy. There we go. We can see practically every second it's trying to open this file. And if I scroll to the right, I have to close this because it's just going to lag my machine. Right? It doesn't find it. So it's searching for this foxitdata.txt file in this path like 100 times a second. It just keeps on searching for it, keeps on trying to access it, which, probably not the best design, but it is what it is. And the first thing I want to check when I see something like this is, can I create this file? Is it something that I could potentially create and then have the privileged process try to interact with? So echo test to foxitdata.txt. It worked. It created. So I can create this file. You'll notice, though, that if I do a directory listing, it's not there. That's because once it tries to parse the file, it just deletes it. And you'll see that in Procmon, but it just happens very quickly. And so the next step is thinking, okay, what is it actually expecting from this text file? And so one of the things I did, it's a bit small, but I'll kind of explain it, is open up Foxit Reader, the update service in Binary Ninja. I do a search for just Foxit data, and that'll take me to this screen where I can see it's trying to open foxitdata.txt here. And then without even having to dive into reverse engineering too much, I can just scroll down and just see if anything else nearby is interesting. And when I scroll down, I see things like session ID. Okay, that could be concerning if I need a valid session. But then I see like stir temp updater path and CS command line. When I see command line, that stands out as potentially interesting because does that mean I can pass it a command line and it'll run it? I don't know. I continue scrolling down, and then I see user shall execute success or user shall execute failed. Okay, that really stands out to me. That means that this has some built-in behavior to execute something, right? And then when I backtrace that a little bit, what you'll find is that the way this passes the text file is it searches for a 2-byte header. I think it's like ff/fe, and then it'll take a path similar to this, where you can have any random session ID. It really doesn't matter. You can put the stir temp updater path to your exe, like cmd.exe, and then you pass it to command line. Like in this case, I'm echoing system to C drive itworks.txt. This is my fake foxitdata.txt file that I create. So to test this, I can place this where it's trying to read Foxit data. Now, as a reminder, in C drive, since I didn't delete it, we still have itworks2.txt, but that's fine because my example is not itworks2, it is just itworks.txt, right? So we'll be able to see if this works or not. So what happens if I just copy that file here? If I just copy that here, obviously that's disappeared because it got passed instantly. And now if I go to C drive, oh look, it works.txt, code execution again. Thank you, Foxit. Right, and that's something that I spotted in Foxit PDF Reader by just opening Procmon and then seeing like 1 million+ requests to this file and wondering, can I create this file? And what is it expecting from this file? What is it passing from it? And this was a 0-day from earlier last year, so it's fairly new enough, right? This one wasn't originally in my talk, but this one I found in the dev VM that I showed that you can pull down from Microsoft. And this one is another 0-day. This one's actually very common in other software as well. I've found this in very, very prominent antivirus software that try to open paths like they go C drive, device, hard disk volume 2, and try to open up DLLs from there, which is just a mistake in the way they're trying to open the path. They're not actually meant to be opening it from C drive device. But because of a coding error, they're opening it from C drive device. And C drive device is a folder that typically doesn't exist, and it's a folder that low-privileged users can create. So this is kind of a take on that by Puppet Labs, or Puppet. I have no idea what this software is, but it comes pre-installed in this dev machine. In, here we go, Puppet Labs, and then it comes Puppet, and it's got like its own Ruby installed and various other things. And literally, I found this a couple of days ago after looking at it for about a second, which kind of drives home my point again that lots of these vulns, they're not hard to find. I download random software, even AVs and very prominent software, and find these things very quickly. Okay. Let me just go back to my slide for a minute. Okay, I think if I open up the one captured at boot, I should be able to find it. We'll find something interesting that it tries to do when it boots. Let's get rid of Foxit reader. Okay, keep going. Should be soon. Okay, well, there's a couple, but I want to focus on one because this thing is just plagued with them. Okay, so, oh, whoops, I still have that there. Let's focus on a different one. Well, anyway, okay, so I haven't cleaned up this VM properly, but in C drive, program data, Puppet Labs, Puppet var lib, it tries to load arbitrary.so. If I go further down, there's actually more, so I don't even have to go with that example. There's here, syslog.so. In C drive, program data, Puppet Labs, Puppet var lib, syslog.so, right? Tries to create a handle to it. If I scroll to the right, you'll see that it's not found. So first thing is, do I have permissions to do stuff there? If I go in Puppet, Puppet Labs, Puppet var lib. And this, I mean, you can pull it down the VM and verify it yourself. It's nothing I've modified, but this folder typically doesn't have anything. And, oh, okay, this VM is cleaned up. It's this Procmon log that shows the wrong one. So here, we actually have write permissions. I can create folders. I can create files. I can create anything in this folder. So I can create syslog.so and things like that. And that means that it's going to, open a handle to it or do something interesting. And I guess I already spoiled it, but the thing is, when it tries to open it, it loads it as a DLL. So naturally, if I put a DLL here, it's going to load it. For the sake of a demo, I'll demo that. Let me just get rid of these two. Oops. Yeah, delete. Okay, so that's fresh. So now I can copy here the DLL I had before. Arbitrary.so, I think, was one of them that it tries to load. That's there. And now to exploit this, I think I can just restart the service. I don't need to reboot again. So we have C driver. What was this one? Something just ran it again. Did it do it on its own? You know what? Let's capture events. Oh. Let me run this again. Sometimes you'll find that. Sometimes you won't have to restart anything. It'll just find it on its own. Oh, I have another Procmon running. Let me modify the filter. I think I need to remove Foxit data again. Okay. go away. Okay. Restart Puppet. And we see it does a whole bunch of things. And if we scroll down, arbitrary.so, so it loads it as an image. We can see that this is a system process spawned by a Ruby command line. And if I go to here, you could probably find arbitrary.so, which lives in the folder we put, and the company's to-do company name is just some DLL I created in Visual Studio. But that's loaded in a system process now, and that means we also got code execution, and there's, our code execution right there. So that's another 0 day in whatever Puppet Labs is, probably some dev thing. It was installed on the VM, so I found that pretty funny. And I guess a key point I'm trying to drive here a lot is that these are so easy to find. Like, I recommend people just pulling down AVs. AVs are a great one because they typically have like 10 executables and all these IPC mechanisms going on and all these shared memory and all these device drivers. And there's just so much going on in them that there's a lot of these attack surfaces for them. But as seen, even something like Zoom, whatever Puppet Labs is, Chocolaty, well, I guess Chocolaty wasn't a vuln, but it was a design decision that we could exploit. Another one, this is my last one, is VMware Workstation. This one is I gotta stop the presentation again. This one is another 0 day in VMware Workstation, or at least a 0 day as of a few days ago, so I mean, probably is still a 0 day. And with that one, if we go add or remove programs after VMware Workstation is installed, and we find VMware Workstation, this one is pretty much like the Zoom one. But you would find it in a different manner, so to speak. So if we go VMware Workstation and we hit modify, this will also auto-elevate the system. So as a low-privileged user, we can get the application to do stuff as system, which means we can be very, I guess, scrutinous in what it does, because everything it does is potentially dangerous if it's doing it as system. If we hit repair, now this takes like a minute because it does a lot of stuff. So I've pre-prepared a Procmon capture of this, just so we don't have to sit through the entire thing. But you could do this yourself in your own time if you wanted to verify it. And what we'll notice is, quick point. So there's one example here where it tries to load this DLL from our app data path. Now the name of the folder is kind of randomized, but there's been vulnerabilities where they'll use a randomized path, but we can race condition this by having our own executable search for newly created folders. And then in newly created folders, we just drop a DLL of this name, such that most of the time we're going to win the race, and when it tries to load this DLL, it will load our DLL. I've had that vulnerability in a lot of other software as well. In this case, VMware can kind of get away with it because the folder it creates with a restrictive ACL that we cannot write to. So I haven't really looked into bypassing this much. Potentially there are bypasses. Obviously, if you create the folder before VMware creates it, that's potentially something. How long is this? 1, 2, 3, 4, 5, 6, 7. It's 7 digits. Potentially, you could create every single folder name 7 digits long, especially if it conforms to like 6 A to Z characters and then 1 number or something. If you find a pattern like that, you can kind of just brute force the folder creation and then run this MSI and then hope that it uses a folder name that you already have existing. And depending on how it handles that, it may not delete it or do something secure. It might just access a DLL from there and you get a priv ask. I haven't actually tested that on this, so I have no idea if that's the case in this scenario. But it's something to keep in mind when you see something like this. But something else interesting happens if we go down. We see that it tries to access this C drive var run VMware hostd ticket. I mean, I'm not sure if that's supposed to be like something it installs on Linux. I have no idea. C drive var run isn't really something that's going to exist on Windows, and it's not something that it installs on Windows, so that's odd. But spoiler alert, when it finds this, it'll do certain parsing. I'm not sure if it's looking for anything else interesting, but I know one thing it does is it'll delete the folder. So one thing we can do to exploit this, again, is do the whole symlink thing where run points to RPC control and VMware hostd ticket points to any arbitrary folder. And when it finds that, it'll just delete it. And that's another arbitrary folder deletion, 0-day in VMware. And like I said, I gave an example before of exploiting this via Chocolaty, just because of the fun fact it was installed, and I found that pretty funny in program data of all places. But there are definitely core Windows locations where you can leverage this as well, so those could be fun to look at too. For the sake of time, I'm not going to demo that one. I already demoed the Zoom version, so feel free to try that yourself if you have VMware installed. If I go back to some of the key takeaways that I had in mind when doing this, is I kind of want to, I guess, demystify the fact that vulnerability research, especially on logic vulnerabilities, which aren't things that are like heavily fuzzed in these applications, especially in some third-party applications like Zoom. I don't know many people that are like logic vuln hunting privasks in Zoom. People will be fuzzing for RCEs and things like that. But some of these other types just aren't heavily looked at. And they are very easy to identify and exploit if you know these kind of mechanisms or these common weaknesses as to what to look at. All the vulns that I've presented in here, all the 0 days and even the end days, took me, most of them, less than a day to go from downloading and installing the software and then finding and actually exploiting the bug. And that is super quick. And these also affect lots of software. Like we saw VMware, we saw Zoom, which is probably installed on most people's machines these days. We have lots of other third-party products that I can't really talk about, but AVs as a general is another big one. But really, like anything kind of is affected by this. It's very hard for me to pull down software and be like, okay, it has no logic vulns at all. And as mentioned earlier, this isn't something unique to Windows. I've found similar things on Mac as explored before, and although I haven't looked at these much at all on Linux and even on Mac, I suspect there are very common logic vulns like this there as well. In terms of the future of these sort of bugs, anyone interested in the hard link side of things, there used to be lots of hard link bugs where you could create a hard link from a file to any other file, even if you didn't have access to that file, like write access to it. And then processes would do things like set permissive ACLs on that file, and that would apply to the file you hard link to and things like that. I didn't really touch on that much because those have been mitigated in Windows by a patch. I think towards the start of last year it might have been when that started to get squashed. And I would actually expect more mitigations to follow, simply because that these types of bug classes, or at least the junctions, like some of the logic things we saw where it just loads a DLL from some directory, I don't think Windows can do much about that. They are trying to do some things around to like the system temp path, but in regards to the junction stuff we saw, the folder level redirection, I know mitigations on that are being actively looked at. So I would kind of expect something around that to be mitigated in the future. But currently, it's something that kind of plagues a lot of software. So yeah, in the meantime, there's still many of those bugs in popular software. Like I said, we saw that C drive var run example from VMware. They also open C drive device or C drive other folders that just don't exist. not realizing, I guess, that low-privileged users can create folders in C drive. And yeah, I hope you enjoyed my talk. That was all I had for today.
Such a great presentation. Really, really enjoyable to see so many 0 days drop in one presentation, so that's really cool. We have a few questions. I believe you've already, the first question that we got, I believe you've already answered this, but I'll just repeat it anyway, and it talks about this person, Risen, I think is the name on Slack. He's asked, Microsoft, he believes, doesn't consider some link abuse vulnerabilities anymore in the latest insider builds. Do you see this category of vulnerabilities disappearing in the near future? And do you believe the mitigation put in place is adequate? I think you've answered that, but did you want to add any more comments?
Yep. So I can't speak, so this is my personal experience. I can't speak on behalf of Microsoft because I don't work a lot in that mitigation space. I know that typically, even with hard links and things like that, typically when you see something like that in my mind where they're not accepting it, it's because they're already looking into broader mitigations as a whole that mitigates the entire bug class, which is why they won't accept individual bugs. But that said, if I look at ZDI and type in junction, I still see heaps of junction-related bugs. I'm not sure if that's just because it's a ZDI thing. I know Microsoft also has some differences between if it's a sandbox escape as well as a just a privask. In my mind, obviously, there's still all bugs that you can exploit, so there's still valid LPEs today, and that's my personal view. But I would definitely expect that just be because that mitigations are coming. But that's just my personal view. I don't actually have any work-related insight into that.
A couple more questions. Can you use MakeLink instead of the Project Zero tools for making those links and junctions?
Yep, so in some cases, yes. In some cases, no. So the MakeLink tool by Windows, I think James Forshaw touched on this as well in some of his blogs, have certain checks in them that restrict what you can do with them, but those checks are in the tool itself. They're not really enforced on like the kernel side of things. So for some things, for some junctions, you can do like MakeLink/J and just point it anywhere. You can create a junction like that. That's true. I typically just use the symbolic testing tools because I remember there being some scenarios where those tools by Google Project Zero don't have certain checks in them that the Windows toolset does. What those checks were from the top of my head, I don't know, but I recommend looking at James Forshaw's blogs because I'm pretty sure he has those detailed in his blogs.
A couple more questions by Nathan Riley for this one. Why are these considered vulns in third-party apps instead of the MSI installer framework?
Yeah, so all MSI, I guess the framework does in this case, is allow the process to elevate the system. Now, if that process decides to use paths in program data or in C drive device or in the user's app data, my personal view is that's the program's choice. The program could easily have operated in C drive program files and its own folder, which low-privileged users shouldn't be able to modify anything in C drive program files. So the fact that it's doing arbitrary deletions on C drive var run VMware hostd ticket, that's not something that I see as a responsibility of Microsoft to enforce. That's something that the programmer who coded up this MSI code in the first place through their custom DLL that lives in there has decided to do. And they could easily decide not to operate on those, I guess, weak paths.
And I suppose that brings us probably to the final question, and I guess you've answered this in part already by that answer that you just gave. And the question is by Will A, and he asks, you said it's a mistake to do file I/O with pre-written paths, assuming the file there is what you expect it to be, but what's the alternative for developers?
Yep, so that all relies on the security of the path to begin with. So when you're running as a system user, C drive is going to point to C drive. If you're running in the context of a specific user account, they can redirect C drive to point to something else. So if you're concerned about that, you can run a system. And then in regards of turning the folders to directory junctions, that can only happen depending on the ACL. So for example, if a process as system tries to access C drive program files, my folder, me as a regular user shouldn't have any control over changing that C drive program files into a junction, because I'll need permissions to modify that folder in the first place, and regular users do not have that permission. If you're operating in C drive program data, then, or even in C drive program files, but where the process has specifically applied a weak ACL, which I've seen before. I've seen programs live in C drive program files, and they've added their own weak ACL to a specific folder path, allowing regular users to modify that folder. And that's kind of their own fault for weakening the ACL. If they want to be sure that it's safe, they should use paths that they either know are hardened by ACLs by Windows, like in C drive program files, or they apply their own ACL on creation and kind of treat it securely like that. If you're operating on directories that by default the user will likely have permissions on in like the user's own app data folder, as we saw Zoom operate on, where it operates on a user's app data folder without any special ACLs on there, that is a known path where users have read and write access to. So that should be known to the developer not to do anything sensitive in there when they're running a system. So that's kind of just something to keep in mind when you're doing those privileged operations.
Yeah, great presentation and great answer to all of those questions. Really like the Slack questions, so keep them coming. But let's all thank Christopher one more time for a great presentation.